It's the longest bridge of its kind, with a single span leaping more than a quarter mile, and a roadway that plunges into a record-setting tunnel. The vision is bold, the challenge is extreme, the plan audacious. How do you design a bridge that will change the map of Europe? What's it take to build one of the world's mega bridges? In Northern Europe, the Baltic Sea converges with the North Sea at the Øresund Strait. It's 10 miles wide with lousy weather. And it's done a great job of keeping Denmark separate from Sweden. The Øresund Strait is a frustrating barrier because each shore has something the other needs. Copenhagen, Denmark needs cheaper housing. Malmö, Sweden needs more jobs. Connect the dots and you could unleash an economic powerhouse. A bridge would make them one big metropolis, but it's never been possible. Until now. Enter the Øresund Bridge, the world's longest cable-stayed bridge that can carry cars, plus the enormous weight of trains. 3,583 feet of road and rail dangling from 160 cables. "200 feet above the sea. The support towers soar 670 feet, jabbing at clouds and making the Øresund Bridge one of the tallest cement structures in Sweden. The equivalent of a 60-story office building. Making this awesome structure had its official start in 1991. That's when Danes and Swedes agreed to bridge their countries. It was a tough pact to negotiate, and now the work only gets harder. Companies from both countries must form a consortium to build the bridge together. The consortium's first challenge? Figuring out how to build a bridge 10 miles long. Immediately, they face a dangerous setback. On the Denmark side, right at the shoreline, is the Copenhagen International Airport, Kastrup. Computer simulations show that building a bridge with high towers would obstruct air traffic. Or worse, building a low bridge would be safer for air traffic, but it would block Denmark's ship traffic. When engineers can't build over the water, they consider building under it with a tunnel 10 miles long.
That would be the beautiful solution, build a tunnel from one side to the other, but that would be the expensive solution. So the third solution that we decided was, of course, to build part bridge and then a tunnel where we were getting close to the airport. A bridge would have been easier or cheaper, but would not have been a good idea for the airplanes.
But combining a bridge and a tunnel poses a new serious challenge. How does a tunnel turn into a bridge in the middle of open sea? Somehow, somewhere, they need dry land for the tunnel to emerge from underwater. They need an island, so they'll have to build one from scratch. When done, Denmark will be bigger by 321 acres. 2.5 miles of tunnel and 2.5 miles of island leaves 5 miles for the bridge. Again, a low bridge is ruled out because of heavy boat traffic, but there's no airport on the Swedish shore. They can build as big as they want. And they need it big, very big. To clear boat traffic, the bridge will have to be at least 200 feet above the water. The center span, at least 1,500 feet long. To meet these challenges with the best possible bridge, the consortium holds a design competition. One of the most spectacular proposals requires building the largest arch bridge in the world.
I think you don't really get an idea of the magnitude of this arch. You might get it from the ship going underneath, but it really is big. It would be a monument of some kind.
But arch bridges have an Achilles heel. As the arch sweeps down toward the water, the clearance for large ships decreases, eventually to nothing.
You always run the risk that a ship could get in there, and therefore you have the risk of hitting the bottom part of the arch, and then the whole thing collapses.
If not an arch, what about a suspension bridge? Suspension bridge technology enables the longest spans of any design. Two enormous cables stretch their length. Shorter cables dangle down to hold the roadway. But connecting cables to more cables makes suspension bridges very flexible. Trains don't do well when tracks bend under their weight.
And railway traffic is so heavy that if you have a suspension bridge, you will find, if you look at it from the side, that the train will always go up a little bulge. It will almost going uphill all the time.
Suspension is ruled out. Arch ruled out. So engineers turn to the one design that can answer all their concerns: a cable-stayed bridge. Its structure is rigid enough for heavy train traffic because the support cables attach directly to the towers. And there is a bonus. Cable-stayed bridges are cheaper to build than suspension bridges. Not having the two enormous main cables saves tons of steel. It's a winner. The best design to meet all the Øresund's needs is a towering two-level cable-stayed bridge, a four-lane highway on top, a high-speed railroad underneath. It will be a monumental structure, the crowning achievement in the 10-mile Øresund link. But there is a ticking clock. The agreement between Sweden and Denmark says the bridge must be completed in 5 years. 5 years to build a man-made island, a record-setting bridge, and the biggest tunnel of its kind. It all starts with the island. The island is the first deadline and one of the most critical. It must be ready in 14 months. Work begins August 17th, 1995. The first rock of billions is placed in the middle of the strait. This stone pile must grow into a 2.5-mile long island, where today there is only water. The first step is laying the perimeter. Large quarried stones are brought in from Sweden. 4 billion pounds of them. 16 barges deliver 40 million pounds a day. To stay on schedule, material arrives 24/7. Each load is carefully placed using GPS. The perimeter is 7.5 miles long. Once it's in place, it's got to be filled. An enormous task. It'll take hundreds of millions of cubic feet of material. Where can Denmark and Sweden come up with that much land? From the bottom of the sea, enter Phase 2, dredging. It's an ingenious win-win solution. Construction crews need to dredge anyway to prepare for the bridge and tunnel. Now they'll have a place to put all the rubble. And it's a lot of rubble. To stay on schedule, crews must dredge an average of 410 million cubic feet a day. This job requires the biggest, most powerful dipper dredger in the world. The Chicago. Its scoop bucket can hold a minivan. Just one pass of its giant shovel digs up 777 cubic feet of seabed. Its floating platform is so big, parts of the Baltic Sea aren't deep enough for it. It has to dredge a lane for itself just to navigate the construction sites. Digging is only the first part of the puzzle. How can crews transport this astonishing amount of dredged earth? The contractor must assemble an armada of 50 vessels. For the pilots, it's dangerous work. It takes expert skill to navigate these huge loads. They fight strong currents, extreme weather, shallow waters. The single biggest dredging job is the trench for the submerged tunnel. 35 feet deep, 150 feet wide for 2.5 miles. That's 70 million cubic feet of seabed. It would be hard enough to dredge it if it were all mud and stones. It's not. 90% is ultra-hard rock called Copenhagen limestone. Even the Chicago can't dent it. So the builders call in one of the most powerful cutter suction dredgers in the world, the caster. The caster's business end is a mega drill bit with 60 cutting teeth. Each weighs 44 pounds. Its menacing appearance deserves the nickname, Spinning Cone of Death. Even with all this firepower, the Copenhagen limestone doesn't surrender peaceably. It destroys 200 teeth a day. In all, they'll replace 52,000. The caster is more than an overgrown drill. It's also a vacuum cleaner. As it chips away the limestone, it sucks up the debris. Then giant pumps force the stones and water through 2.5 miles of pipeline, all the way to the island. The shards of limestone are so abrasive, they erode the inside of the pipe. Moving all this rock and mud brings an extra challenge not faced most other places. Protecting the environment. It's especially vulnerable in the shallow Øresund Strait. The biggest threat is from plumes of debris. These clouds can kill huge swaths of seagrass. Seagrass that feeds and shelters all the marine life here. For Denmark and Sweden, hurting the environment is a deal breaker. They make a pact. No more than 5% of the debris can spill, or all dredging must stop. This would put deadlines in jeopardy, the entire project at risk. 5% spill doesn't sound like a lot till you do the math. That's 12 million cubic feet of misplaced rock. It's a balancing act between speed and caution. Throughout the dredging, workers succeed in protecting the environment, but they don't realize there's another danger. One that threatens their own lives. November 25th, 1995, the 30th day of dredging for the Øresund Link. Digging up the 247 million cubic feet of seabed seems to be a straightforward assignment. The crew thinks everything is going smoothly. They don't realize dredging has become the most dangerous work of the entire project. Workers don't know they are inches from death. The Chicago has accidentally scooped up a dangerous payload, a bomb that's ready to explode. It's dumped onto a barge, covered in mud. Nobody knows it's there. But if anything bumps its detonator, 80 pounds of TNT will blast the barge and crew to pieces. How it ended up here is a story that dates back 60 years. May 1945, Denmark celebrates the end of World War II. The British Royal Air Force puts on an air show over Copenhagen Harbor with live bombs. Some sink without exploding. 6 decades later, they're more deadly than ever.
Even though the bomb is maybe 50, 60 years old, it can still work as designed. So that's why it's dangerous, always. If the bomb has gone through some corrosion and there has been some deterioration of the explosives, it may have become even more sensitive, and in that case, even more dangerous.
Equipment inches closer to the bomb. Then, just in time, someone on the dredging team spots it. The Royal Danish Navy is called in to remove, defuse, and explode the bomb. These bomb experts know there could have been a tragic outcome.
If they hit the bomb with their dredgers or with their buckets or whatever, and it went off, somebody had been killed.
It was a narrow escape for the crew and the schedule. With the bombs gone, dredging resumes, but the relief is short-lived. More bombs are discovered. Luckily, no one is injured, but it's a direct blow to the schedule. No area can be dredged until it's swept for bombs.
Before the dredging was completed, we had found 16 bombs in total.
All 16 are moved and destroyed. Being safe is more important than being on schedule. Long before the bombs were discovered, even before a dredger dipped its first bucket, Øresund engineers knew they faced a unique set of very difficult challenges here. The water separating Denmark from Sweden is 10 miles across, but the gap between these sovereign nations is much bigger. They are very different countries with different languages, currencies, and different ways of doing just about everything. Cars didn't even drive on the same side of the road until the 1950s. Trains still don't, passing on the right in Denmark, on the left in Sweden. They run on different electrical voltages. The signals mean different things. The radio frequencies aren't the same. None of this mattered until now, because the countries have never been connected. It's a puzzle that needs to be solved before the bridge can open. Engineers need to design a computerized Rosetta Stone so the different train computers can communicate. They need to create a standardized wording so all train operators understand spoken instructions. And designers have to invent electrical equipment to switch trains from 25,000 volts to 15,000 volts on the fly. The solutions are so complicated, every new train will need to be tested without passengers before it can use the Øresund link. And what about emergencies? Firefighting equipment in one country doesn't fit equipment in the other. The best solution? Putting both couplings on every water hydrant. Every little detail requires collaboration. The countries don't even use the same name for the strait. The word Øresund is cobbled from the Danish and Swedish versions. Well, some of the team works on a name for the link. Others continue to work on how in the world to build it. the plans call for a submersible tunnel bigger than any ever made. The first step is constructing a factory to make tunnel parts. The idea is to make the tunnel in 20 segments, then assemble them in the trench. Even the segments break world-size records. They're 577 feet long, 127 feet wide, and 28 feet high, with 2 tubes for traffic, 2 for rail, and 1 for emergency escape. They need to turn out 1 enormous segment each month for 20 months. In Denmark, tunnel construction begins with reinforced steel bars, 88 million pounds of them. They're bent and welded into a huge steel cage, then slid into an enormous mold. Now the massive framework is encased in concrete. More than 2 trillion gallons of the stuff. But it's not just any concrete. This has to last 120 years underwater. The formula has to be exacting. Even the amount of water mixed in is critical. Too little, and it won't be durable. Too much, and it won't be watertight. Of all the monstrously large parts of the Øresund link, a tunnel element is by far the biggest. It's nearly the length of 2 football fields and as high as a 3-story house. This single piece weighs an astronomical 121 million pounds. Moving it is dangerous, an enormous challenge, and it triggers the most catastrophic accident of the entire project. Building the tunnel for the Øresund link requires 20 tunnel segments. Each weighs more than 24 space shuttles. And they contain enough concrete to build a sidewalk around the Earth twice. No technology in the world can lift one into the air and put it in place. So how can you move 121 million pounds off dry land and into the middle of the Øresund Strait? You turn it into a raft and sail it. First step, plug the holes with giant steel panels. Each panel weighs about 7,000 pounds. Now this gigantic concrete structure could float. But how do you get it to the water? You don't. An ingenious lock system brings the water to it. The end of the assembly line is surrounded on 3 sides by dikes. A huge movable wall closes the 4th side. And the basin is flooded to more than 30 feet above sea level. It takes 262 million gallons of water. Even afloat, it takes 4 50,000-pound winches to move it, and 2 more winches to steer it to the deep end of the basin. When the water returns to sea level, the element is ready to head out. It takes 4 tugboats to tow the element. That's 40 Ferraris worth of horsepower. When it's over the trench, there's a new challenge: sinking it. It's harder than it sounds. How do you force a raft this big underwater? The trick is ballast. Water is pumped into special tanks. It has to be done slowly and evenly to keep the element horizontal. 4 massive cables help guide its descent. Precision is paramount, so it can be connected to the rest of the tunnel. Winch operators use GPS and depth gauges to keep on target. The margin of error is less than ½ an inch in any direction. Divers install a temporary frame to help guide it. When it reaches the seabed, winch operators pull it tight against the previous segment. Seawater trapped between the segments is pumped out, and the steel panels are removed. To keep the tunnel from ever floating again, concrete, 3 feet thick, is poured the entire length of the roadway, and boulders are piled on top. The system works flawlessly for the first 12 elements, but the 13th still gets special handling. It's officially renumbered 12A. Superstition trumps logic. Unfortunately, renaming won't be enough. Tuesday, August 4th, 1998. Wind and current conditions in the channel are perfect. Tow out of the new tunnel element is uneventful. By noon, element 12A is guided into position. At 3:30, pumps add ballast, slowly sinking the unit beneath the waves. Suddenly, something is very wrong. It starts tilting. Then, all hell breaks loose. A huge explosion of water blasts 100 feet into the air. It plunges to the bottom. Crews on the pontoons shut down all power, fearing they'll be electrocuted. It's hours before they figure out what happened. Human error. A steel plate wasn't sealed correctly. Water pressure forces it open and floods the element. The winches can't hold the added weight, and the segment plunges. Luckily, no one is injured. But what about tunnel element 12A? Extensive testing confirms it's usable, but valuable time is lost. Oresunds builders could have chosen a different method to build their tunnel. They could have bored a tube under the seabed. And that's just what Denmark did, 2 hours down the line from Copenhagen. Here, the rail and road need to cross a channel called the Great Belt. It's also here that Denmark has a disaster far worse than the Oresunds. To dig their 2 train tunnels, the Great Belt brings in 4 enormous boring machines. Each almost 300 feet long. The front end is a 250 million pound drilling head, 24 feet across. The cutting head chews up soil and boulders. Then an auger shuttles ground bits and pieces to a conveyor belt that dumps it on a small train. As the tunnel boring machine works its way underground, it also installs pre-made wall segments, 62,000 of them. The problem with boring is the ground can be unpredictable, and that's how disaster strikes the Great Belt. The boring machine hits a water pocket. Water drips in, then pours. A special safety hatch should contain the flood. It was left open. Water floods one tunnel, crosses through emergency tunnels, and floods the second. It takes a year to get back on track. The tunnel here is different from the Oresunds in another way. It goes all the way across, so heavy trains won't use the bridge at all. This gives engineers more design options here than at the Oresund. They can build a suspension bridge, and they do it in a big way. The world's second largest, it leaps nearly 9,000 feet in a single bound. The towers reach up 833 feet, almost 100 feet taller than towers on the Golden Gate Bridge in San Francisco. Unlike the Oresund, this bridge's structure depends on 2 main cables draped over the towers. These monster cables are 3 feet thick and almost 10,000 feet long. The main cables are actually made up of over 18,000 wires, each thinner than a pencil. They're not twisted together. They're just stretched next to each other and bundled. The finished cables weigh over 21 million pounds each. The trick to making a suspension bridge is anchoring each end of the cable. For the Great Belt Bridge, the anchor blocks are enormous, little islands unto themselves. Each weighs more than 700 million pounds. Cable-stayed bridges, like the Øresund, don't have anything like this. Anchor blocks are just for suspension bridges. But you can't just bury the cable in the concrete. It'll pull right out. You have to spread the load over a huge area. That's why, as the cable enters the anchor block, the wires branch out into smaller and smaller clusters. By the time the cable reaches the concrete, the load is spread over 690 square feet. In the anchor block, it's easy to show off the cable's flexibility.
You can move it with your hands if you want to. It would take a little time to, but it will actually start to move. Now it's moving a little, 3 or 4 millimeters, but it's moving all the way from the top and down to the anchor plate.
This is just the kind of flexibility the Øresund Bridge needs to avoid. The Øresund needs to be rigid to carry the tremendous weight of car and rail traffic. And it needs awesome engineering to break world records. Having to build the bridge section this high and this huge creates the biggest challenge of the entire Øresund project. The Øresund link is hurtling full speed toward the July 2000 deadline. The last stones have been placed on the artificial island. Tunnel elements are sunk. Now it's time to build the world's longest cable-stayed bridge for car and rail. Construction starts with the towers. They are by far the highest freestanding double-legged bridge towers in the world. 60 stories. 2 giant legs are connected by a massive crossbeam just below the roadway. Above the deck, just open space. A crossbeam above the road was nixed to keep the bridge looking lean and clean. And for another reason, plane crashes. If this computer-animated disaster were ever to come true, freestanding towers would help the bridge survive. Common sense might suggest just the opposite, but the engineers say a design without crossbeams above the road keeps the towers more flexible. Less of the impact will be transmitted to the rest of the bridge. It'll stand a better chance. Building the towers actually starts on land. Like the tunnel segments, the foundations are made in a dry dock, and they are huge. Each has a footprint covering 1/3 of an acre. Enough land for a house, garage, and backyard. Their dead weight is over 40 million pounds. That's way lighter than the tunnel segments, but moving these mountains are a lot trickier. They are 74 feet high. The Øresund Strait is only 25 feet deep. You can't just float them like a raft. You need to carry them. No vessel can do this, so Øresund engineers must build one. They start with 2 immense barges, then connect them on both ends, creating a kind of catamaran. Now the dry dock is flooded, so the catamaran can sail over the foundation. It takes 5 enormous tugs to tow this contraption into the channel. At the bridge line, the foundation is lowered into a pit, already dredged into the seabed. GPS helps guide it to within 3 inches of target. The foundations stick out of the water 11 feet. Now each stump must grow another 600. Each becomes its own self-contained construction site, outfitted with enough equipment for a small factory. The 2 legs for one tower climb into the sky in 13-foot sections. One always stays 40 feet ahead of the other, so their massive cranes don't get tangled. When the towers reach 145 feet, time to add the crossbeam. Then at about 262 feet up, a steel box to hold the stay cables is integrated into the leg. Another box is added every 40 feet. From the outside, the towers look solid. Actually, they're packed with equipment, including an elevator. A hatch in the top of the tower brings you to the penthouse view. While the towers are being built in the middle of the Øresund Strait, the double-decked spans are being assembled at shore. They are immense steel and concrete boxes, about 460 feet long and 75 feet wide. The top will be the 4-lane highway. The train goes inside. The designers decided to put the train tracks in a special cement trough. If a train ever derails, they hope this liner can keep the train on the bridge. The bottom of the spans may look solid, but like the towers, they're hollow. It's a human-sized gerbil habitat, housing equipment critical to the bridge. Squeezing through chamber after chamber reminds you that there are 178 million pounds of steel in this bridge. Steel that has a mortal enemy, rust. It can destroy the bridge from the inside out. Paint could add protection, but it's not economical to paint so much surface area. Instead, the Øresund Bridge has a vast system of dehumidifiers. They keep the air inside below 60% relative humidity. No moisture, no rust. Regulations require crews to inspect every part of the bridge, a prudent measure. But a big challenge. How do you inspect the underbelly of a bridge 200 feet above water? Even on the road, how do you protect your workers without interrupting car and train traffic? Luckily, Øresund engineers planned ahead. Hanging under the bridge is a spectacular motorized gantry. The Øresund Link has one of the very few gantries in the world that can run the entire length of the bridge. Most gantries would be stopped at the bridge towers. But this gantry pivots to squeeze between the supports. On the other side of the tower, it spins again and continues on its way. Once the crew is where they want to go, the Øresund's gantry is like a gigantic Swiss Army knife, packed with exotic contraptions. A hydraulic arm can carry a worker outside the trusses, even up and over the roadway. The access is phenomenal, but more importantly, train and car traffic aren't interrupted. Hanging hundreds of feet over the water, the arm gives access to equipment like this device, created especially for the Øresund Bridge. It's a damper to reduce cable vibrations. Vibrations that can shorten the life of a bridge by decades. The gantry has another gadget used to inspect the towers. It's not for wimps. This hanging bucket can lower workers 200 feet, clear down to the water line. Sometimes to check the concrete for cracks, sometimes to change light bulbs that guide ships through the navigation channels. From the gantry, it's easy to see the deck was assembled from pieces. It's less obvious how the pieces got here. They are enormous, and they were pre-assembled miles away on shore. The good news is that they only weigh 12 million pounds, not 40 million like the foundations, or 121 million pounds like the tunnel elements. The bad news is that the tunnel and foundations were lowered into place. The bridge spans need to be lifted. How do you hoist 12 million-pound spans 200 feet up and hold them dangling in the air? By any measure, the Øresund Link is one of the most ambitious engineering projects of the 20th century. The contractors have already built from scratch an artificial island, 5.5 miles around. They've ground through 2.5 miles of ultra-hard Copenhagen limestone. And they've pieced together the world's largest submerged tunnel. With only 1 year left in the schedule, it's time for the final stage of construction, and the most spectacular. The bridge will finally start looking like a bridge. All the planning, all the calculations will be put to the test as the main span is put in place. It needs to be high enough for ships to pass under, strong enough to carry speeding trains and cars. No one has ever built one like it, this gargantuan. To do it requires the largest floating crane on Earth, capable of lifting more than 16 million pounds. The equivalent of 30 Boeing 737s. She's called the Swan. And this is the Swan's moment of glory. The Swan must summon 75% of her strength to lift each span. The highest span goes right next to the tower. Crews attach cables. The first cable is 167 feet. Each new cable must be longer than the one before it. The longest will be over 800 feet. The Swan brings in another span. The roadway cantilevers further from the tower and closer to a world size record. This is the most vulnerable time for the bridge. Temporary scaffolding helps, but the bridge won't be up to full strength until all the pieces are in place. Wind and storms could be disastrous. Each pylon leg gets a full 40 cables. The whole bridge has 160. That's 4.3 million pounds of cable. On August 14th, 1999, the Swan installs the final roadway span on the bridge. Denmark and Sweden are connected for the first time. Denmark's Prince Frederik and Sweden's Crown Princess Victoria meet at their first ever border crossing. For 9 years, the construction deadline has loomed over everything and everyone involved in creating the Øresund Link. Finally, on July 1st, 2000 at 11 p.m., the Øresund Link officially opens to business, on time and on budget. It's an engineering feat, a fiscal feat, and one that stuns lawyers everywhere.
We managed to build this link across the border, and we never ever had a lawyer in our office. We never had any disputes with anybody. And that really was amazing when you think about it, that you can spend some $3 billion and you can do it without the interference of lawyers.
The bridge may be open, but the challenges don't stop. It has to pay back every penny it spent, one toll at a time. The official budget for the bridge, tunnel and island approaches $3 billion. And the expenses never stop. There will always be maintenance. Not long after the link opens, engineers discover a problem with the guardrails. The bolts are corroding. One bolt's no sweat, but there are 16,000 of them. If they fail, a minor fender bender could turn into a death plunge. Crews must act now to prevent the bolts from rusting through. It's a big job, but it's better than waiting and having to replace the bolts. That would require tearing up the concrete. Stopping the corrosion starts with removing the nuts and blasting the bolts clean. To keep out moisture, crews coat the bolts with gel and use better fitting washers. 2 down, 15,998 to go. The maintenance and everything that happens on the bridge is monitored in Sweden from a building near the toll plaza. Hidden inside is a high-tech command center.
Traffic center, Army. Okay, he's coming to work.
30,000 points of information from the bridge feed into the control room computers. Operators constantly monitor safety.
If something happened, the first thing we have to do is, if it's a huge thing or a big accident, we have to close. We also close the bridge when we have a strong wind or if we have like ice on the road.
There are 256 cameras on the link. Too many for operators to monitor, so a computer helps. It can recognize stopped cars or cars going the wrong way. When it spots trouble, it alerts operators and shows them the appropriate camera. Operators can also manually control the cameras, which have incredible zooms.
My favorite camera to showing how much we can see, this is this one, where you can see at the McDonald's the people they're eating. That's a yellow packet, so they're eating like a Big Mac, I think.
Keeping their eyes on the bridge has given operators an appreciation for the incredible physics at work here. Like when the man stopped his car in the emergency lane.
He wanted to get something from behind in the car, so he opened the door, saw a truck coming, so he didn't shut the door, he just held it towards him. But as the truck passed, there was a vacuum after him that tore out the door and brought it 50 meters along the bridge.
They also see people acting strangely, but that's strictly off the record.
What naked people would that be? Yes, I saw some naked people once. People do funny stuff, but we let it be with that.
One of the Øresund Link's pleasant surprises can't be seen from the control room. It's underwater. The 51 bridge piers have had an unexpected environmental impact. They've become artificial reefs, covered in mussels and plants, providing food and shelter for sea creatures. Environmentalists who were originally against the Øresund project now document the explosion of life. Creating a fixed link across 10 miles of the Øresund Strait has been a dream for generations. It was a monumental engineering effort, pushing technology to the absolute limit and establishing new world records from the coast of Denmark to the coast of Sweden. The largest submerged concrete tunnel in the world. The world's longest double-deck bridge for car and rail traffic. The tallest freestanding double-leg pylons on any bridge anywhere in the world. In its first 5 years of operation, more than 44 million people crossed the Øresund Link, going to new jobs, to new homes, or just exploring. The Øresund Link changed the map of Europe, successfully bringing 2 cities, 2 countries, and an entire continent closer together. It stands as one of the world's mega bridges.